The ANS, short for the Arabian Nubian Shield, occupies extensive areas of northeastern Africa and the western side of the Arabian Peninsula, and it's comprised of a number of geologically distinct terrains representing a mosaic of accreted late Proterozoic island arcs. The ANS was formed during a period of widespread tectonic and thermal activity approximately between 1200 and 450 million years, commonly known as the Pan-African orogeny, that is further divided into Lower, Middle, and Upper Pan-African. The Lower Pan-African spans from 1200 to 1000 million years and is characterized by thick sequences of tholeiitic basalts and andesites of immature island arcs with greywacke carbonates and cherts. These rocks are tectonically deformed and metamorphosed up to amphibolite facies, and they were intruded by composite batholiths of gabbroic to dioritic composition dated at about 900 million years. The Middle Pan-African, between 1000 to 650 million years, is responsible for the bulk of the rocks exposed in the ANS and is characterized by the deposition and emplacement of lithologies that can be defined as belonging to one of two tectonic settings. Mature island arcs consist of thick sequences of calc-alkaline volcanics like basalts, andesites, dacites, and rhyolites, and pyroclastics interburied with volcaniclastics, mudstones, cherts, quartzites, and carbonates, or oceanic crust or ophiolitic rocks that form linear belts of serpentinized mafic and ultramafic complexes associated with paleobasalts, argillites, tuffs, cherts, greywacke, and marbles, and they are interpreted as abducted oceanic crust marking sutures between accreted terrains, seen to post-tectonic plutonic rocks of calc-alkaline composition intrude these sequences, which are commonly arranged in linear belts and form 50 to 60% of the outcrops. As for the Upper Pan-African, from 650 to 450 million years, it's characterized by accretion and cratonization, and as such marks the final stage of the Pan-African tectonism in the region. Rocks of this stage include rhyolitic and dacitic lavas with subordinate andesite and pyroclastic deposits. Interburied with these volcanics are clastic and carbonate or marble rocks, and they are alkaline to calc-alkaline in nature. Post-accretion magmatism products represent a change to alkaline and para-alkaline plutonic to volcanic magmatism characteristic of within plate setting, and they may have been derived from the partial melting of calc-alkaline protoliths. These rocks include an overwhelming abundance of granites and granodiorites, alkali granites, and quartz-bearing alkali feldspar cyanide, minor gabbro, diorite, monzodiorite, tonalite, cyanite, and monzonite, in addition to minor nepheline cyanide, and it's believed that this magmatism must have had a role in controlling magmatic hydrothermal mineralizations. in order to place the deformational history in the NS within a regional tectonic framework, the following scenario was proposed. Rifting of supercontinent Rodinia at 900 to 850 million years led to the formation of the Mozambique Ocean. An intraoceanic arc and back arc basin complexes were created together to form the juvenile material in the ANS between 870 to 690 million years. The terrain accretion resulted in the formation of arc sutures between 800 to 700 million years. These sutures are oriented east to northeast in the northern part of the shield and north to northeast in the southern part. The east to northeast trending sutures share a common structural scenario in which subhorizontal ophiolitic nab structures were steepened due to deformation by upright faults associated with collision between terrains. The north to northeast trending arc sutures are marked by ophiolitic naps, which were sometimes overprinted by north trending upright faults and or strike slip faults. These faults are either developed as a result of an oblique collision between terrains or represent a younger post-accretionary deformational phase between 750 to 650 million years. The closure of the Mozambique Ocean led to the collision of the ANS with the rifted blocks of East and West Gondwana along north trending arc continental sutures. The western boundary of the ANS is defined by north trending sutures marked by fault and thrust belts in the south and sinistral transpressions in the north, and it suggested that the eastern boundary of the shield is defined by two parallel sutures. The continuation of convergence of east and west Gondwana resulted in crustal shortening in the NS, which was localized along north trending linear belts that offset the east to northeast trending sutures in the northern part of the shield and was superimposed as a coaxial deformation on the north to northeast trending sutures in the south. The shortening deformation culminated with the formation of northwest trending sinistral and northeast trending dextral strike slip fault systems at 640 to 540 million years. In a nutshell, it may be said that drifting of a Proterozoic supercontinent took place prior to 950 million years, and between 950 and 630 million years, an ocean basin existed along the northeastern margin of Africa where active subduction, island arc development, and accretion of oceanic and continental domains took place. This tectonic history of the ANS enables us to analyze the environmental conditions of ore deposition, since an understanding of these environments is critical to any evaluation of the mineral potential of the area. With that said, there are at least 3 tectonic settings and related hydrothermal mineral deposits that can be considered. Number 1, hydrothermal deposits associated with ocean floor spreading Number 2, deposits related to subduction and island arc formation. Number 3, deposits related to post-tectonic igneous activity. Ophiolite suites are common in the ANS, and as they represent segments of abducted oceanic lithosphere, offer good targets for base metal mineralization of the mid-ocean ridge exhalative type, as well as magmatic chromite and nickel sulfide deposits. In the ANS, however, the most important metallogenic domains in terms of frequency and economic importance are the assemblages of volcanosedimentary and plutonic of the accreted island arc terrains, volcanogenic base metal sulfide deposits, and hydrothermal vein-hosted precious metal deposits are in fact abundant. At a minimum, 3 styles of mineralization have been identified. The first is represented by lens-shaped massive sulfides, usually hosted by felsic pyroclastic rocks containing mainly pyrite and sphalerite with variable amounts of chalcopyrite, galena, sulfur salts, oxides, and tellurites. The second consists of pipe-like stockwork deposits occurring within chloritized, silicitized, and silicified volcanoclastic assemblages, and the main ore minerals are pyrite and chalcopyrite with minor amounts of sphalerite, galena, cubonite, and oxides. The third style is represented by base metal sulfides occurring within a system of quartz veins containing relatively high gold and silver values. The final metallogenic epoch related to the Pan-African tectogenesis in the ANS is typified by a number of rare element deposits like niobium, zirconium, yttrium, thorium, rare earth elements, tin, etc., associated with post-tectonic alkali granites. This mineralization represents, in most cases, the products of alkali metasomatism related to the crystallization of late-stage residual melts. Rare earth elements provide the most important exploration target associated with these post-orogenic alkali granites.